Hi, this is Gordon Parker from Michigan Tech, and in this video I'm going to solve some inverse Laplace transform problems. Before we do that, let me do a quick motivational example. Let's say that we have a first-order differential equation in y, and its input is a step function with an amplitude of 2 times that 1 of t function. And let's say it has an initial condition of -1. So what we're going to do is solve this differential equation using Laplace transforms, and in the process we'll have to do an inverse Laplace transform. So let's take the Laplace transform of this differential equation, sy of s minus y0, don't want to forget that initial condition, 3y of s equals 2 over s. Let me factor out this y of s, and I'm going to just leave it as y now. I'm not going to keep dragging around the function of s business. So we have an s plus 3. I'll substitute in this initial condition. Whoops, my pen is not, there we go. Plus 1 equals 2 over s. And let's go ahead and bring that 1 over to the other side of the equation. 2s minus 1, which is equal to 2 minus s over s. Great. Now we can solve for capital Y. So we have 2 minus s over s plus 3. Now, y of t, the solution to the differential equation, is just the inverse Laplace transform of this expression I just created. So we've converted the problem of solving a differential equation from a calculus problem just to an algebra problem, doing a inverse Laplace transform, which really means we do a partial fraction expansion and then look up some pieces in a Laplace transform table. So let's go ahead and do the inverse Laplace transform. First, we have to break this expression up into factors based on the denominator. So we have a c1 over s plus a c2 over s plus 3. Before I go too much farther, I can actually write down the solution in a little bit of an open-ended way, but I know that I'm going to have a c1 step there plus c2 e to the negative 3t from this factor, and this whole thing times the unit step. I could put a box around that and say I essentially have my solution. I don't know exactly how these things are weighted, the C1 and the C2, but I have at least I know the form of the solution. So all we have to do now is find these two coefficients, C1 and C2. So let's do that. I'm going to just bring this down a little bit so we can still see how we broke things up. Okay, to get C1, I can obtain it by taking y, multiplying it by s, and then setting s equal to 0. And the reason I'm setting s equal to 0 is because that factor has to do with a root at 0. So let's see, what do we get from that? Maybe I need to back up just a little bit more. There we go. So when I multiply y of s by s, it cancels this s, and so we get 2 minus s over s plus 3. Let s equal 0, and we get 2/3. Wonderful. C2 is equal to y times s plus 3. You let s equal 0. And let's see, if we come back and look at this, we can see that we'll have a 2 minus s. Oops, I messed something up here. This shouldn't be s equals 0, that should be s equal negative 3. It has to do with that root, the root at negative 3. So here we get negative 5 over negative 3. And so here we get 2 plus 3 over negative 3 equals negative 5/3. So now we have the solution to our differential equation. Let me go up one, and then I'm just going to hop down. Here we go. So y of t is equal to, let's see, we have a 2/3 there. I'm going to factor out the 1/3, and we'll have a 2 minus 5 e to the negative 3t multiplied by that unit step. So there it is. But let's go ahead and check that. Let's check the initial condition first. If I set t equal to 0 in this equation, I get 1/3 times 2 minus 5, and that's equal to negative 1. Boom, I got it. The next thing to check is to see if this equation satisfies the original differential equation. And the original differential equation was y dot, plus 3y equals 2 times that unit step. So if we calculate y dot, we'll get, let's see, we'll have a negative 5/3 times that. So we'll have 5 e to the negative 3t. And then if we stick that back into this and take our solution and stick it in there, we should see that it comes out to just be 2. So let's check it. 5 e to the negative 3t plus 3 times our solution. Well, this 1/3 cancels out, so we get plus 2 minus 5 e to the negative 3t. And lo and behold, that's equal to 2. It checks. So what we did here was solve the differential equation using Laplace transforms as a motivating example of why we're interested in these inverse Laplace transforms, and did an example. So now let's do another example. We'll do a couple more, but we won't get into the whole differential equation thing. We'll assume that maybe we're working on a differential equation and we ended up with this rational function in S, and then we want to inverse Laplace transform it. So here's an interesting one. So the first step is to break this up into pieces based on the denominator. We can see here that we have a root at 0, and then we have this thing. Let's see, we should check to see if it's complex or if we can factor it. So if we take this and square it, we get 16 minus 29 times 4, and that'll be the square root. So certainly that's negative, and so yes, it is complex. If it wasn't complex and we could factor it, then this would be the time to factor it. Okay. So now that we know that that's complex, we know that y is going to break up into 3 pieces. We'll have a c1 over s plus a c2, and this depends on the Laplace transform table that you're using. I'm using one where the complex roots are represented this way. And we have this denominator again. Oftentimes, a lot of tables will have this term as a negative instead of a positive. But this is what we're using. So, okay. Now, what I need to do to round this out a little bit is to figure out what a and b are from this complex number. So I need to put s squared plus 4s plus 29 into completed square form. My a is just 1/2 of that coefficient, so I get that, and then I just have to figure out what this thing is, and it's squared, and that'll give me b. So if I look at this first term, I have s squared plus 4s plus 4, and I have to look at what I need to get up to 29. That's 25 plus 4 is 29, and so I need a 5 there. Okay, so now I know that a is 2 and b is 5. Great. Again, I can pretty much write down the solution. y of t is going to be c1, I'll put some brackets out here, plus c2 e to the negative 2t cosine 5t plus c3 e to the negative 2t sine 5t multiplied by this unit step. Beautiful. I now see the form of the solution. It jumps up with a step of amplitude c1, and then it has a decaying exponential sinusoidal response. Now all I have to do is find c1, c2, and c3. So let's go after those one at a time. c1 is going to be my original y multiplied by s, because that c1 is associated with the root at s equals 0, and then I let s equal 0. And so what that gives, and maybe I should jot down, I'll just jot down here what our original y was, 6s squared minus 15s plus 116 divided by s squared plus 4s plus 29. Great. So I take this y of s, multiply it by s, so that cancels this thing, and then let s equal 0. So I get 116 over 29. So that tells me that c1 is equal to 4. Boom. Done. Now I can substitute that back into the expansion that we had on the previous page. So I now know that coefficient, and if I group the two terms that I had over the second order polynomial, I'll get an c2 times s plus 2 plus 5 c3, that was our a and our b, a was 2 and b was 5, over s squared plus 4s plus 29. That has to equal that. I shouldn't have really crossed this s out. It didn't go anywhere from our y of s. So those two y's have to equal each other. The denominators are already equal, right? I could take this and get a common denominator and certainly get that denominator. So the key part now is the numerators. So I have to make sure that this numerator is equal to that one. And the way I'm going to do that is by picking the appropriate c2 and c3. So let's go ahead and take this and get a common denominator, and then we'll be able to compare numerators. So the numerator of this y of s, once I go to a common denominator, do the cross multiply business, is that plus, I need to multiply the s by this whole expression. So I'll have a c2s squared plus 2c2s plus 5c3s. And that numerator has to equal 6s squared minus 15s plus 116. Now s is a complex variable. It can be any value, 2 plus 7j, etc., etc. So that means that these two, the left and the right hand side of this equation, have to equal each other for all values of s. So what I have to do is make sure that the coefficients of like powers of s match between the left-hand side and the right-hand side. So let's go ahead and do that. I'm going to say, I'm going to pull out that 4 and pull out that c2, and that has to equal 6. Those are all the s squared coefficients. Now we go on to the s coefficients. So 16 plus 2c2 plus 5c3 has to equal negative 15. And actually, when I did this, I already now know that c2 is equal to is equal to 2. Perfect. All right, I can just solve that equation for c2. And I can actually just solve now this equation for c3. Right, because I'll have 16 plus 4 plus 5c3 equals negative 15. 20 plus C3 equals negative 15. So C3 equals negative 35. Oh, that's a 5C3. Whoops. There we go. So 5C3 equals negative 35. So C3 is equal to negative 7. Done. Now notice I've used up all my S coefficients. I should have checked that one off too. But there's one coefficient I didn't use, and that was the constant. And the reason I didn't need it is because we already solved for this C1 and plugged it in. However, it gives me a nice check in my algebra from this equation. It's just kind of a minor check in this particular example. But sure enough, 4 times 29 is equal to 116. So it checked. There's a good chance I at least did some of the math right in that expansion. Okay, so that's the end of that example. We could write out the whole thing now, but it doesn't bias a whole lot. So let's do one more example. Okay, so how about y is equal to s squared minus 12s minus 8 over s plus 2 squared and an s squared plus 1. This example has a couple interesting features in it. First, it has a repeated real root here, and it has a complex root here that's actually just pure imaginary. So let's expand this out. Because of our repeated root at negative 2, that's going to give us a couple pieces. All right, those two. And then I'm going to get since we know that this is complex, actually it's imaginary, but I'll pretend I don't know it's complex just yet. And I'll just write it out as if it was strictly complex. So C3, s plus a over s plus a squared plus b squared plus C4b over that same thing. Great. Now the normal approach, and we'll use that here also, is that we would solve for a and b. We'd write this in completed square form. Well, it already is in completed square form, right? What this says is that a is equal to 0 and b is equal to 1. Okay, so now I can write down the solution. From this term, I get a C1 t e to the negative 2t. From this term, I get a C2 e to the negative t. From here, I get a C3 cosine t. And from here, a C4 sine t. And I'll multiply the whole thing by the unit step. Look at that. I can now see what the response looks like. It has a couple exponential terms. This one is multiplied by t, so maybe it's going to go up for a little while, but then it'll eventually squish back down because the e to the negative 2t will definitely annihilate any polynomial in t that it's multiplied by, as long as you go out far enough in time. However, this term tells us that the response is going to oscillate forever. Right? That term will never decay in time. So as you go out to, let's say, time equal infinity, there's going to be some sort of a sinusoidal response. So I can get a lot of information just from looking at that. But to be complete, we should figure out what C1, C2, and the rest of them are. So let's go after C1 first. C1 is equal to our original y times s plus 2 squared, and then you let s equal negative 2. So we get 4 minus 12 times negative 2, so that's plus 24. And then what else do we have? A minus 8. And it's divided by, if we remove that and let s equal negative 2, we get 5 here. So So 28 minus 8, that's 20 over 5. So C1 is equal to 4. Boom. So far, so good. Now, we could plug that back into here and then kind of brute force C2, C3, and C4. But we can also go after C2 directly using a partial fraction expansion strategy for repeated real roots where we use differentiation. So let's go ahead and do that. C2 is equal to DDS of y times s plus 2 squared, and then you let s equal -2 again. Okay, so that's DDS of, let's work all this out, s squared minus 12s minus 8 over s squared plus 1. And we'll have to let s equal -2 eventually. Okay, so we have to do DDS of that. We could use the quotient rule. So the derivative of the top is 2s minus 12 times the bottom, s squared plus 1, minus derivative of the bottom, which is 2s, times the top, boom, divided by s squared plus 1, quantity squared, let s equal -2. Okay, we're getting there. So let's go ahead and put in s equal -2. So here we'll get -4 minus 12. So we'll have a minus 16. That's this term multiplied by this thing, which is going to be 5. S squared plus 1. Minus 2 times s, so that's going to be plus 4. Then we'll get a 4 plus 24 minus 8. All divided by s squared plus 1. So for this, we'd get 25. So let's keep going. 16 times 5 is 80, so we have minus 80 plus, let's see, 28 minus 8 is 20 times 4, so plus 80 over 25. That's nice. So C2 is equal to 0. Wonderful. So we have two of the coefficients, C1 and C2. Now we'll plug those back into our y of s and solve for C3 and C4. So what do we have so far? We had C1 was equal to 4, so 4 over s plus 2 squared. Our C2 is 0, so we can forget about that one now. And then we have a C3. It would be s plus a, but a was 0, so C3s plus C4 times b, but b was 1, so that's nice, divided by s squared plus 1. And that whole thing has to equal our original rational function, which was that. So we do the same thing that we did on the previous example. We'll get a common denominator of this expression on the left-hand side. Once we've done that, we can just compare the numerators. So I'll just cut to the chase and go right to the numerators. The numerator for this, once we get a common denominator, is 4s squared plus 1. Whoops. Plus s plus 2 squared times the quantity C3s plus C4. And that has to equal this numerator, which is s squared minus 12s minus 8. I'm going to go ahead and multiply out that left-hand side, just because there's quite a bit going on. Let's see, here we have an s squared plus 4s plus 4 times C3s plus C4. Go one step more in multiplying this out. I'll do that one first. Plus C3s cubed plus C4s squared. Now I'll do that one. Plus 4 c3s squared plus 4c4s, and finally that one, 4c3s plus 4c4. And that has to equal this. The coefficients of like powers of s between the left-hand side and the right-hand side have to equal. So let's start accumulating equations that will make that happen. I look at this, I scan this equation, and I see that the highest power of s is s cubed. So I have now that c3 on the left-hand side has to equal the s cubed power of that, which is 0. Wow, that was an easy one. So c3 is 0. I just have one more coefficient to get, and that's c4. So let me check that off. So let's go after the s squared terms. I'll have a 4 from that, plus c4 from this, plus 4c3 here, and that has to equal 1. So what this tells me, since c3 is 0, is that c4 is equal to -3. And I'm done. Now I didn't use a couple coefficients here, but I could check them. So just for fun, we could go 4c4 plus 4c3, that's these two. Is that equal to this, -12? Well, let's see, c3 is 0, c4 is -3, so yep, that checks. Then the last check we could do is the constants. 4 plus 4c4, is that equal to -8? Let's see, c4 is -3, so 4 minus 12 equals -8. Yep. So high probability that all of this was done correctly. Okay, so now we've done 3 examples. They all seem to check to whatever checks we had, but let's do one more check. We'll go ahead and use MATLAB to check them. It'll just take, maybe another minute or two. Okay, so here I have MATLAB open, and I guess I lied a little bit because I said we were going to use MATLAB. But if you're fortunate enough to have one of the MathWorks toolboxes that allows you access to MuPAD, then we can use MuPAD. It's a symbolic equation manipulation code, and we can use it to do all kinds of things, including inverse Laplace transforms. So let me define y. Y equals, I'll do the last example first. In the numerator we had s squared minus 12 times s minus 8. And in the denominator we had s plus 2 quantity squared, and we also had an s squared plus 1. And that looks about right. And so now we can go ahead and take the inverse Laplace transform with the ilaplace command. So I give it the rational function in s, which is what we called y. I have to tell it what variable it is a function of and what variable I would like the inverse Laplace transform to be a function of. And there it is. And lo and behold, I believe that's exactly what we got on the previous page. Our C1 was equal to 4, C2 and C3 were 0, and C4 was -3. So there it is. The other example we did, so I'll do another one, y was equal to, let's see, in the numerator we had 6 times s squared minus 15 times s plus 116, and in the denominator we had s, and we also had s squared plus 4 times s plus 29. Looks about right. And now let's do that one. It's a little bit harder to see, but let's see. We have, there's our 4 that we had for our C1, and then we had a 2 for the C2, And we had a -7 for the C3, which is this -7/2 multiplied by 2. Perfect. So it gives you just a very quick way to do inverse Laplace transforms. Of course, you can go the other way too, Laplace. So up here I had said that this was y. Just name it something. I could also go Laplace y ts, and I get that big thing. And I could go ahead and use MuPAD to get a common denominator and compare it to what we typed in up here, and we'd see that it's the same. Okay, so what we did are several examples, 3, of inverse Laplace transform. Actually solved a differential equation along the way, and then looked at using MuPAD to check our work. So again, this is Gordon Parker at Michigan Tech, and thanks for watching.